Hi everyone, we are back and let's go through our Pset 2 solution. So for A through C, I identify what type of conventional unit cell is present, simple cubic, we've got FCC, we've got BCC, and we've got nothing there. Number of atoms, 1, 4, and 2. So there we go, number of atoms. Number of nearest neighbors, 6, 12, 8. There we go. Nearest neighbor distance is always 2r. The lattice parameter, a is equal to 2r, a is equal to 2r root 2, a is equal to 4r over square root of 3. So lattice parameter. The next nearest neighbor distance is always for BCC a, FCC a, and for SC 2r square root of 2. Atomic packing factor 0.74. Oops, 0.74 here. Oops, let me erase that. So it's 0.74, and for everything else, it's less than that. Less. Here we go. Are any of these cells close packed? Yes, FCC. Are any of these cells primitive unit cells? Yes, simple cubic. So FCC is close packed, simple cubic is primitive. There we go. All right, that's number one down the drain, effectively. So let's keep moving. Determine the crystallographic directions in A. Oops. So let's determine the crystallographic directions in A. So if I look at this atom here, for example, so let's go ahead, or that direction. So my finish is 0, 0, 1. My start is 1, 0, 1. So that leaves me with 1 hat 0, 0. Makes sense. If I go over here, my finish is at 1, 1, 0 minus my start, which is at 0, 1, a half, which is going to leave me with basically 1, 0, 1 hat, half, which I must do now 2, 0, 1 hat. There we go. Let's go over here. So my finish there is 1, 0, 0 minus my start, which is at 0, 1, 1. So that's going to leave me with 1, 1 hat, 1 hat. And then finally this guy over here, my finish is at 1 half 0, 0 minus, let's call this 1, 1 half 0. So that's going to leave me with basically 1 hat, half, 1 hat, and then 0. So that's going to leave me with 1 hat, 1, 0. There we go. Those are all the directions. Are any directions close packed? That depends on the cell. So for this cell, it'd have to be the basically the family for simple cubic. So for SC, it is 1, 1, 0 or 1, 0, 0. Those are the family. For BCC, so for this cell, it would be 1, 1, 1, and for this cell, it would be 1, 1, 0. So this would be a close packed direction only. The rest of them are not. There we go. All right. So we've learned about those close packed directions, close packed planes. Let's erase this here. Erase, erase, erase. Let's get those going. All right. We've got this. Determine the crystallographic directions. What else are we doing here? All right. What are the close? So we got this. We got this out of the way. All right. Identify the crystallographic planes. Okay, so here we go. So cross our origin here. So I'm going to set my origin here. Back. So this plane will now be basically -1. Intercept is -1. I take the inverse. What is that? Because x positive, x negative, and then the rest of them are all going to be 0, 0. For here, I'm going to keep my origin. What's my intercept? Well, x is going to be a half, y is going to be a half, z never. So my plane is 2, 2, 0. There we go. Origin. Any of the planes close packed? Nope. The only close packed planes, we don't have a close packed planes, simple cubic, BCC, FCC, the only one is R111. Excellent. Calculate the planar density for the plane in C. Well, PD, planar density, equals number of atoms divided by the area, but there's no atoms, so that planar density is 0. That was a quick one. Draw BCC cell in D. So BCC. BCC. Draw the -1, 1, 2 direction. So is this direction close packed? Definitely not, because it's not the basically 1, 1, 1 direction. So nope, as we will see in a second. So let's draw that direction. So finish. So I need this to be basically a half. So this will be 1/2. Oops. 1/2 1, and then that will be 1/2 0, and then 1 will be 0, and then 1. So this is my finish. This is my start. So I'm going to do 1/2. 1/2. That's my finish. And then my start is going to be basically 1, 1, 0, 1. So it's going to be here. So my direction will go right to there. So that's my direction. Draw the OO2 plane. That will just be simply this. There it is. Calculate the planar density of this plane. Is it close packed? So I know here, if I project that plane, I've got one atom in here. My A for BCC is equal to 4R over square root of 3. So now, time to take out my old friend Mathematica. So let's go ahead. Oops. So take out Mathematica. Let's do that. A BCC equals 4 times R square root of 3. So we have planar density pi times R squared divided by ABCC squared. Oops. Not to 22. 0.589, and that will be our value. So is it close packed? Nope, as we expected. All right, so let's kind of zoom out here, scroll up. So I need to draw the following directions in the unit cell below. So they need to be contained in the cell. So let's go ahead. So 3. So I need to do basically everything in a third. So let's do this one first. So 1, 1, 3. So I need basically, let's call this, I'll do it 1, then 2/3, 1, 2/3, and then 1, 0. So 1, 1, 1 is going to be our finish, and then we're going to do 2/3, and then 2/3, right, or 2/3, 2, oops, 2/3, 2/3. So I'll make it like this. It'll look like that. Finish minus my start. Not super pretty, but there we go. 1 minus 2, 1. So same thing. So finish and start. So let's do, we'll call this a half, 0. Actually, let's do 1, 1/2. 1, 1/2. We'll call this 0, 1, and then we'll call this 1, 1/2. So that'll be your finish. So 1, 0, 1, 0, 1, and then we'll start with 1/2, 1/2, 1, 1/2. So basically like this. Oops. It's another possible one. Again, there's lots of different answers that can be done for this. I hate grading this problem set because it's infinite solutions. So let's see, I'm gonna make this 0, 1, 1, 1/2. I'm gonna do the 0, 0. And there we go. So that should be, yep, that'll give us what we want. Actually, I need to flip it. 1/2 here, this 1. All right, so now my finish is going to be here. And then I'm going to go 1, 1. So it's going to be like this. There we go. We got it. Draw the 2 in the other planes. So let's do this. So my intercepts are going to be effectively, for this one here, it's going to be -0.5. It is going to be 1, and then it's going to be -1. So I already know I'm going to have to switch that origin because I have negatives. So how am I going to draw this? So I need to go back. So let's start off picking my origin like here. This is my new origin. So I know I'm going to intersect -1 as such. I am going to go to the -1/2 x right here. And then I'm going to do, the +1. So I need to switch my origin. See, this is why you kind of draw it out in real time. So -1, -1/2 x, and then y is 1 here. Connect the dots. There you go. That's your plane. What about 0, -1, 1? Again, I'll do that. Let's say do that right here. So 0, that's an infinite. -1 here, 1. Then I do the same thing here. And then done. There you go. Let's look at PDF for platinum. Correct the first 2 peaks, and what is the integral in the first peaks? Well, we need to look at what platinum is. So let's go ahead and decrease our screen. So I'm going to look at platinum. And in my periodic table, I know, where is my platinum? I have my crystal structure. So platinum looks to be FCC. So if it's FCC, I know, and then the metallic radii is 1.39. So my metallic radii is 1.39. 1.39 angstroms. So what do I know about this structure now? So platinum is FCC. That means it has 12 nearest neighbors. So the integral under the first peak, this integral must be equal to 12. And I also know that this represents my nearest neighbor distance, 2r, and my next nearest neighbor distance is equal to my a, which is equal to 2r root 2. So I could just calculate those right now. So the value of that first peak on the x-axis should be 2 times r ptt, and the second one should be 2 times square root 2 times r pp. This right here, and voila, we've got it. So there we go. Those are the corrections. Those are your solutions. Pset 2 done. So look forward to seeing you next time on Pset 3. Thanks. Have a good one. Bye.